All right, welcome AP students to your gas properties and gas laws kinetic molecular theory pre-lecture. You guys have just learned theoretically about IMFs, and now we're going to take in this Unit 3 topic, we're going to take a look particularly into gases. Remember, Unit 3 in the AP is considered the most heavily weighed unit. It's about 18 to 22% of questions, at least theoretically. And it's kind of like actually a hodgepodge of various topics. So we have IMFs that we've already talked about. We're going to look at the gases, and then we're going to look at solutions and solubility. So it's kind of just all of these various interactions between particle subtopics. So as far as gases go, gases have some common properties amongst themselves. Gases have really low density, considering that they're very widespread in a given amount of area, right? Or volume, and many are colorless and odorless. Okay, many, not all, as we know, are colorless and have no odor. Sorry, morning handwriting. They can form solutions. So remember, actually, I don't know. I think we covered this in Unit 1, but a solution is a mixture of anything. So we can have a gas mixture, and it's actually a homogeneous mixture, right? You can't see the different particles. You can't see the different parts. So they can form solutions or a homogeneous mixture in any proportion. And I'm just going to write homogeneous to remind you. They have demonstrate, or they allow us to examine a relationship between volume, temperature, and pressure. So the way that we describe the behaviors of gas is through the gas laws and theories of motion. We're going to tackle the theory of motion in this pre-lecture, and then we'll tackle the laws in class. So the first postulate, or the first principle in the kinetic molecular theory, or KMT theory of gas particles, is that gases have no attractive or repulsive, okay, forces. So essentially, according to this theory, in order for us to assume and apply it well, we basically have to ignore the presence of IMFs. Okay. Now, obviously, we know that there were intermolecular forces between the gas particles, but considering the general nature of gases to be one quite far apart from one another and quite a high kinetic energy, we can kind of create a scenario to make the conclusions that we need to make and identify the patterns that we need to identify, where we can just assume that there are essentially minimal, if not negligible, IMFs. Okay. In addition, we assume in the kinetic molecular theory that the gas particles have negligible volume. Gas particles have negligible volume compared to the distance between B/W, means between the gas particles. So the idea here is that the mass is essentially negligible. The mass and the volume, right? Then the nature of its matter is essentially negligible. And then third, we assume in this theory that molecules, or gas, specifically gas molecules, right, are in constant, rapid, random, straight line motion, i.e., they could be described through physics vector motion, and collisions, therefore, are elastic. So if and when there's a collision, no energy is lost or transferred. Okay. And of course, there's no IMFs when they do collide. There's no sticky nature to it. And then finally, we say that kinetic energy is going to be proportional to the temperature. Now we know that temperature is a measure of kinetic energy. And if we assume that collisions between gas particles are elastic, we can assume that the temperature or the kinetic energy being represented by that temperature is directly related. And we don't have to worry about something disturbing it or something removing a percentage of that energy. We don't have to worry about overestimating or underestimating based off of temperature. Just a quick reminder about kinetic energy. The equation is kinetic energy of some particle in motion equals a half times the mass of the particle, the velocity of the particle squared. Okay. We have this distribution curve right here that kind of shows us for a given amount of energy demonstrated by the particles, we see the percentage of those particles in the sample, and that would be, wow, I don't know why I'm getting so confused. Let me rephrase that. We have a graph right here, a curve that's kind of like a standard deviation graph, okay, like in calculus or pre-calculus, where we have kinetic energy on the x and percent of particles that demonstrate that energy on the y. So when we take the surface area underneath the curve, we can identify the percentage of a given sample of gas of particles that is traveling at a given energy and therefore velocity as well, right? If we know the mass of the sample, which we can always find figuring out the molar mass using the periodic table. So anyway, wow, I don't know, that was so hard for me to get out of my mouth. So we call this curve, by the way, the Maxwell-Boltzmann distribution curve, discovered by Maxwell Boltzmann. Woo, right? And I realized I wrote too big. Maxwell, oops, Boltzmann. Okay, and this graph or this distribution curve shows us that the average kinetic energy of particles in a sample of matter. All right, so what we just saw up here. And what particularly it's useful for is it shows us the relationship, okay, between, I realized I did not pull up. Okay, so just the relationship between mass of the particle and energy. All right, and here's why. We can graph a Maxwell distribution curve for a given sample against another sample, and how the curves differ when we overlap them tells us something about the particle size. And the larger or heavier a molecule is, okay, the slower it moves to create the same amount of kinetic energy. And the smaller molecule, okay, the faster it moves to create the same amount of kinetic energy. So if we were to put two samples, right, and overlay them where we're putting them in the same temperature environment, so the same kinetic energy environment, and then we graph the Maxwell-Boltzmann distribution curve, we can identify which molecules are heavier and present as well, and which are lighter and present. We could also graph according to change in environment. So we could stick a sample, the same sample, in two different environments. And what we'll see according to the Maxwell distribution curve, okay, is that at higher temps, we of course get a curve that will shift to the right, okay, because the particles, a greater percentage of the particles is moving at higher kinetic energy. So a greater percentage of particles, okay, is moving at higher energy. Okay, on the other hand, at lower temperatures, right, we see a shift left. And what we would identify is that greater percent of particles is moving at lower overall energy, right? So one of the biggest mistakes that people make is that they see the height of the curve and they're like, oh, moving faster. But remember, don't forget to read your axes. It's saying that blue line is saying at a lower temperature, a greater percentage of my particles, okay, is moving at a lower kinetic energy range. Whereas the red, even though it looks more broad and it has a lower y-axis height, what it's saying is that a greater percentage of my particles, okay, is moving at a higher range of energy. Okay, so be careful when you read these that you don't confuse and the stereotypical image of height as being explicitly and directly connected to better or worse or faster or slower. Okay. So when do we see gases behave in an ideal manner? So there's this law called the ideal gas law that we take the kinetic molecular theory, and from it, we develop this mathematical equation between the concepts or the properties of volume, temperature, and pressure with a given amount of gas. The kinetic molecular theory gives us a big indication or a big very solid foundation to develop the relationship between temperature and mass or the amount of gas. But what we really want is a equation that relates all of it. And so that's where we're going to get into tomorrow is the ideal gas law. But remember, with the kinetic molecular theory, we had a lot of assumptions about gases. One of the main ones is that there's no IMFs. So we call this ideal behavior. So when a gas is called an ideal gas, okay? When a gas is called an ideal gas, we are assuming the necessary behavior aligned with the kinetic molecular theory principles or postulates. And so what that means is, when do we see a gas behave in an ideal way? When do we see a gas behave as assumed in the KMT, kinetic molecular theory? We see this at extremely low pressures and high temp environments, which, by the way, makes sense. If we are in the kinetic molecular theory, our basis for the ideal gas law that we'll talk about tomorrow, our basis for developing a mathematical relationship between volume, temp, pressure, and amount of gas, okay? And if we look at our postulates and we are assuming that one, gases have no attractive force, okay? They don't engage in any IMFs. They have essentially negligible volume take up compared to the distance. Low pressure means less condensing of the particles, means far more space and spread out between each particle. And we're assuming that when they move in straight line vector motion so that collision is essentially elastic. We assume then that the faster they move, we're probably going to see more elastic-like behavior because they'll collide and they'll basically collide so hard that sometimes when you collide so hard that you just kind of go past each other, right? It's like the trick of pulling out the tablecloth from the table. If you do it fast enough, it's almost like the particles don't have time to catch up to realize what's happening. So it makes sense that we see this ideal-like behavior, this KMT postulate assumption behavior at really low pressures and high temp. Okay. In addition, it's really helpful when gas particles have super low mass. It also helps them behave more ideally. Okay, or in a way that aligns with kinetic molecular theory that allows us to then take the equation that I will introduce tomorrow, known as the ideal gas law, and apply it effectively. All right, so that's your pre-lecture. Pretty short. Sorry about stumbling over my words so much. Sometimes I've had these kind of videos, but good luck, you guys, and you're doing great. Bye.